Thank you for giving me the opportunity to present my work. I'm Pawel Gora, and I'm going to talk you through a project that I did as part of INZNAK, Professor Czyżewski's team at the Gdańsk University of Technology, and I want to talk you through about a traffic management method using variable speed limits, where speed can be adapted to traffic conditions, weather conditions, driving conditions, or the road network. This is really something close to what Adam Kurowski was discussing, and I also used the same methods and tools, and Adam has done a good introduction into that. My angle was to develop a method for traffic management, which would be to suggest specific speed limits on variable message signs and where those signs should be located. The motivation behind this, I think everyone understands the problem of road accidents. More than 1 million people are killed worldwide annually, and more than 20 million are injured. And the majority of accidents are caused by speed, whether it's speeding or going over the limit or not adjusting the speed to the conditions, whether it's bad weather or limited visibility. So one way to approach this is to use variable message signs with variable speed limits, and such variable speed limits can help to harmonize traffic. And rather than have acceleration and deacceleration or overtaking, we can hope for a smoother traffic, reduce accidents and casualties. Existing approaches to traffic management using VSLs, well, at least the best methods, usually take into account traffic conditions, but they hardly ever include weather conditions or road surface conditions. And so the goal of the research is to fill in this gap, meaning producing a method to help reduce speeds as a result of the weather or traffic conditions. Right, the methodology. There are two phases. First of all, we have to identify where such messages should be placed. And once they have already been installed there and the detectors are in place, then we have to manage these speed limits using adaptive control. So how can we evaluate this? Obviously, we cannot test everything under real conditions. That's costly and possibly dangerous. But one good approach or a standard is to use traffic simulation. And the simulation environment I used is the Sumo software, which is an open source software. Adam mentioned that too. So how can we propose speed limits, or how do we make our decisions on where to locate variable speed limits? There are several things to include. Just as Adam said, our job is also to set the distance, which would be a safe distance. So, for example, when we have the average distance between vehicles, where we look at vehicle density and vehicle length, average vehicle length, these are things we can measure using detectors, and then restricted visibility, and then response time from the driver when there is an incident, maximum delay in the braking. So using this and the formula, we can determine the maximum speed at which we can be moving in a specific place to be able to stop the vehicle over a specific section, given the traffic conditions, whatever they are. So well, response time could be constant, or average vehicle length could be constant, but delays or safe distances for braking, well, that could depend on the weather and the road conditions. Things can get even more complicated when we're driving on a curve, because it's about friction, and also there are different speeds, especially when you look at the radius of curvature. And you also have to include friction. So that's how we can define the maximum speed. So I ran an experiment on a road section. This is the Droga Kaszubska road near the village of Wieżyca. What's characteristic of that road is that it has several straight sections where you think there is no hazard, but there's a pretty sharp curve marked as U-turn here. We can put up several detectors and several variable speed signs, and then apply the method that I've explained. Once we know the default initial maximum speed for the vehicles, well, under pessimistic conditions, where vehicles are going at maximum speed, and then looking at the curvature and the roadway conditions, we can then determine the maximum safe speed on the curve. And then, using standard formulas, we can calculate the safe braking distance, starting from the initial speed given the road conditions, and we want the vehicle to reduce its speed to a speed that is safe on that curve. Well, the radius of curvature here is 25 meters. And I worked based on pessimistic conditions, the worst possible conditions, so with snow cover. And so it was A equal 1.5 meters per square second. So the speed should go down to 20 kilometers per hour from 90 kilometers. And so using the formula, it shows that the vehicle should start braking around 200 meters ahead of the curve. Now, if they start braking 200 meters before the curve, this could be quite a sudden action, and again, could be dangerous. But so to ensure safety, this could be more of a phased-out process. So they should first go down to 60 kilometers, but between the beginning of the curve and the first variable message sign, there should be an additional sign, and our calculations tell us it should be 82 meters from that sign. At this point, they should slow down to 20 kilometers per hour. There should be an additional variable message sign at the end of the curve so that they can resume the speed which is right for the traffic density. And we also need detectors in the 3 places where we have variable message signs, and in 3 control points, which is at the beginning, at the curve, and at the end of the section. So we use the SUMO program. We analyzed different weather conditions with snow, and we also looked at normal conditions, so it was snow, rain, and normal. We also tested different traffic conditions, looking at density from 400, 800, and 1,200 vehicles per hour. For each case, I conducted 20 simulations when the control system was enabled, and 20 times with the VSL disabled. Each detector calculated speed throughout the simulation. We then had the minimum, the mean, and the maximum speeds and the median. And after we had had 20 runs, we were able to see the deviation of these values, both from maximum, minimum, and mean. So we had 54 charts, 6 detectors, 3 weather conditions, 3 traffic conditions. Well, we were able to see the differences, the speeds under different conditions. What would be the speeds if there were no systems to control the speed, and what would be the speeds if the system is there? So at the beginning of the section for detector D1, the differences aren't very big, but then for D5, which was in the very center of the section, the differences could be significant. And what we find is that when conditions are very bad with snow and very bad friction, we could find out that 80 kilometers per hour, as suggested by SUMO, could be dangerous. So 20 kilometers per hour, which is what we know from calculations, well, perhaps could be too low. It really depends on what the constant parameters are. But the method can clearly suggest different speeds as opposed to the simulation. So we've had a number of experiments, and what I noticed in the detectors is that the method works in the sense that variable speed limits reduce speed limit as measured by the detectors. And this is consistent with the speed limits proposed by the system. And the speeds away from the curve also showed variable speeds depending on traffic volume, which suggests that the method should be viable, especially using the Klaus model. And it's obviously based on specific assumptions, and it seems that it would be a good idea to develop and improve the method. But we do understand that these are just initial results, and the experiments were conducted in a simulation environment. And certain values were default values. They were not calibrated using real data regarding the road Droga Kaszubska. So clearly more work needs to be done before the method can be applied in practice. Well, thank you very much. And finally, I'd like to say thank you to Professor Czyżewski and all the other people in the INZNAK project team. So thank you to Mr. Hoffman, Adam Kurowski, and Szymon Zaporowski. So thank you for sharing the knowledge with me and helping me use the tools as part of the INZNAK project. Thank you.